Okay, picking up from the last video where I left off, I said I was going to attempt to implement antiderivative anti-aliasing measures for a tan function. So I did that, and I ran into issues, weird kind of glitchiness trying to do it with my function tabulator, but while exploring this, I've come up with some more interesting questions. So I want to just run through what I've been working on this evening, if anything else. So, Bella oscilloscope, here I have a waveform coming in from tides, mutable instruments tides, and I'm comparing hyperbolic tangent with this antiderivative method. So you can see I have a gain term on it, and it saturates, and they look pretty much the same, right? If we go into the spectrum, you can see some interesting stuff. So let's get right there, and then if I sweep through the frequency, you can see the blue trace is the antiderivative one. You can see it's already slightly more attenuated at the high frequencies, and as I increase it, see right there, all of that reflection off of the sampling frequency, the Nyquist limit that you're getting on the pink trace, which is just normal tan H, it's attenuated. It's still present, but it's attenuated on this other version. So you can see, like, it dives down pretty nicely. It's pretty good attenuation. And then I was reading this paper. It's screwed up because of that. So I was reading this paper where I'm getting this algorithm from, and they say naturally, okay, you can do first order, but naturally second and third and fourth and fifth, all of the higher order antiderivatives are better. And attenuate, as you can see here, attenuates more of the harmonics, aka I guess a steeper filter, if you can put it in those terms. So I went into Desmos and I wanted to explore what that looks like. What do the higher order antiderivatives look like? Or does integrals, that's what they are. So you start out with the the first order one here, and then I love this function. You can do indefinite integrals in Desmos, and interestingly enough, the integral of the natural log of cosine h is like it's like a sine. It's like a hyperbolic sine kind of shape. I forget what you call those. And then, so let's just go through the orders, and then the next order up, it's kind of odd and even. And then odd and even. You can see if I put them all up on the screen, they're kind of getting wider and kind of more saturated around. There's more of a dead zone at the origin. So if I take that to the fifth and the sixth order, we can see we get this saturation. It's kind of interesting looking curve. Anyway, this sparked my memory because something I was working on before is I wanted to be able to scale linear values from 0 to 1. So for example, a linear potentiometer, 0 to 1 value, and when I have it in code, I have it in 0 to 1. I want to be able to scale that range exponentially or logarithmically, kind of bend it one, but within that range. So I figured out this function over here, this 1 minus exponential over 1 minus exponential, does that job. So you can see I have two versions of it. And if I just zoom in here, we can see at this, as A approaches that, it's almost linear. So you can see it's going basically linear, and then it kind of bends. I'm going to get the other one out of here just so you can see just this. I can bend it one way, then in the middle, it's pretty much linear, and then I can bend it the other way. And I figured out, okay, so that's nice. And then this was a couple months ago. I was like, oh, I can actually use this to approximate sigmoid type functions, because like the hyperbolic sine, like I was just describing. So you can see if you were to add these two together, then you end up with kind of that it's approximation. And then if you go the other direction, you get kind of a sigmoid type. So bending one way gives you one thing, bending the other way gives you the other thing. Anyway, so I wanted to see, noticing that there's a trend as the higher order antiderivatives get you a more and more kind of saturated curve, but it's this shape, and I was like, I'll have a parameterized version of this shape that I can bend. Like this, to me, looks very similar to this. So now if I overlay them on each other, so ignore this mess, but these are the ones that I want. So I can, again, do an odd and an even version. I don't know what that means as far as the, what that actually does to the sound, but anyway, so you have this. I'm just going to get rid of the ones that like that. Okay, so just comparing these two, this is my 6th order antiderivative compared to my function, just this thing, and then added with the inverse of itself. And so if I control that bend parameter like I did before, kind of shrinks it in, and then it does this wild stuff when I go. But if I'm just going to bound this to just 1, or yeah, because this kind of, you can see it saturates out, and I think this is like an approximation of the process of taking the antiderivatives, because you see this kind of, and then the gain, this, and it scales. They don't scale the same way with the gain, but I think that can be compensated for. But the point is, I can use this function, so I tabulate this function, which I know I've already done. I know I can do that. Use it to create this approximation of this high order antiderivative, and then use that for the anti-aliasing. So the same thing that I just showed on Bella, but do it with, instead of having to do all these integrals and layers of stuff, I can just use this one function, which is a close approximation of the high order integral, but I only have to just put it in a lookup table and read from it, interpolating if I want. But if I can just save enough samples, I don't even necessarily need interpolation to reach the same level of accuracy as the CMath representation. So anyway, that's just a little overview. I know it's not a ladder filter, like I said I was going to do, but that's coming soon. This is just, I was kind of picking up my code back where I left it off a couple weeks ago, and wanted to explore this paper, ran into this interesting little nugget here, and I'm like, now I'm going to experiment with this, and then once I can get this high order antiderivative anti-aliasing on my saturator function, then I can use that saturator in, say, a filter or whatever other structure. And there is the question of stateness, because this does involve subtraction. Like if I highlight these lines here, it's, you're subtracting, so you're doing you're using the unit delay in there. So I don't know if you can just pop that right into the middle of a filter structure, and I think maybe you can't. But again, if I can use this other function to approximate it, I don't even know if that matters. The point is, I think I can get very good performance for very cheap out of this function here, because I can bend it one way, I can bend it the other way, and it approximates everything I need to. So that's what I'm exploring next. Just a little update for you.